Hello guys, welcome on Tesla Adventures. I have changed the theme of the videos and I have turned on the dark theme to prevent the unwanted radiations on the eyes of the students. So I hope you are liking this dark theme. Now today in this video, we are going to discuss a very exclusive concept of JEE Advance as well as for Olympiads. In fact, once in JEE 2016 paper, a question based on this topic was asked in JEE, and later on it was considered that some part of that question is not in the scope curriculum of JEE. But we will be discussing that question also later in this video, and we'll be discussing that complete section, that how to find out the angular momentum of such rolling motion of cone or some other body. Now starting from this situation, you can see that there is a cone which is rolling with this axis fixed and this point fixed on this axis, and you can see that it is rolling like that and it is turning also. So if you can imagine the complete motion of this cone, then you can see that this cone is moving in a circle whose radius is h. The center of mass of this cone is moving in a circle whose radius is h, as well as this angle is theta, this is theta, and this is radius r. Now you can see that due to the pure rolling, you will be observing this center of mass with moving with some velocity vcom, and this center of mass when it is moving, you could see that this point and this point would be at rest, and if you join these points with a line, then it would be instantaneous axis of rotation. We are referring IAR, we are referring this axis as IAR due to the fact that we know that IAR is the locus of all those points which are at rest and they are associated with the object. Okay, so this is the IAR. Okay, now which means that these points would be at momentarily rest at all the times. Therefore, you can write, you can also see that the center of this cone is rotating about this blue axis, which is this axis. This is y axis, let us suppose, and the center of this cone is rotating about this blue axis with angular velocity of omega 1, and this cone is also spinning about this red axis, which is x axis. This is x axis, and it is rotating about this axis with the angular velocity of omega 2. And obviously we can see that the resultant of these two omega would be along this IAR, and we can summarize the complete motion of this cone along IAR using only rotational motion approach. Okay, so now we can prove this fact that why we are taking this as IAR. We can write that VCOM, this is VCOM, so VCOM is equal to h omega 1. You can write that VCOM is equal to h, which is the distance of center of mass from this axis, perpendicular distance, into omega 1 is the angular velocity. Now you can also see that this position, this point is at rest because it lies on IAR. So we can say that it is also instantaneous center of rotation. So we can also write VCOM as r omega 2, because this cone is spinning about this axis with the angular velocity of omega 2. So let us assume that there is a disk which is spinning with angular velocity of omega 2, and it is its center is moving also with some velocity VCOM in such a way such that VCOM is equal to r omega 2, so that we can say that this disk or this ring is in state of pure rolling. So first of all, we can see that h omega 1 is equal to r omega 2. So this is the first equation which we can write. And to prove this fact that this is a IAR, we can find out the VCOM through this axis. Now first of all, you can see that the resultant of omega 1 and omega 2 is this omega resultant, and therefore omega resultant can be written as omega 1 sine theta plus omega 2 cos theta, because this angle is 90 minus theta and this angle is theta. So omega resultant is omega 1 sine theta plus omega 2 cos theta. So omega resultant is omega 1. Now tan theta, you can see that tan theta is r by h. So tan theta is r by h. So cos theta would be equal to h upon under root of r square plus h square, and sin theta will be equal to r upon under root of r square plus h square. So you can substitute these values here and you can see that omega 1 sin theta is r upon under root of r square plus h square, plus omega 2 can be replaced by omega 1 by this equation 1, and we can write omega 2 as h omega 1 upon r, and cos theta is h upon under root of r square plus h square. Now you can see that omega resultant is equal to, you can take the LCM, and this would be omega 1 multiplied by under root of r square plus h square divided by r. You can solve this expression, you can verify by yourself, divided by r. Okay, so you can see that this is sine theta, so I can write that omega resultant is equal to omega 1 by sine theta. Now you can see that VCOM, if we write down VCOM by IAR, then we need to find out the perpendicular distance of center of mass from IAR, and if this angle is theta, then this would be 90 minus theta and it would be theta. So this perpendicular distance from IAR would be equal to r cos theta. So I can write that omega VCOM is equal to r cos theta into omega r, and VCOM is equal to r cos theta into omega r. Omega r is omega 1 by sine theta. Okay, now you can see that tan theta is equal to r by h. So you can replace r with h tan theta, and sine by cos is already tan theta, and this is omega 1. So it is h omega 1, and we have already written this result. So you can see that the velocity of center of mass by all three axes, calculated by all three axes, by this blue axis, by this red axis, and by this IAR is same, which should be the result. Okay, so now let us discuss the alpha, angular acceleration of this cone. Now you can see that this cone has mainly two angular velocities. This is omega 1 about this blue axis, and this is spin angular velocity about this red axis. We also term this omega 1 as orbital angular velocity. So you can see that if the magnitude of omega 1 and omega 2 are constants, which are constant in the question, so you have to find out the angular acceleration. Now angular acceleration would be the rate of change of the resultant angular velocity. So if I write down that omega resultant is equal to the vector sum of omega 1 and omega 2, and alpha would be d omega resultant by dt. So alpha would be equal to d by dt of omega 1 plus omega 2. So you can see that this omega 1 is not changing in direction as well as it is constant in magnitude. So omega 1 is constant, and therefore d omega 1 by dt, d omega 1 by dt would be 0. Now alpha would be equal to d by dt of omega 2. Now you can see that omega 2 is constant in magnitude, but it is only a variable in the direction, because when this cone will rotate, the omega 2 will also rotate. Let us see the top view. If we carefully observe the top view of this cone, then we can see that when this circle is the locus of center of mass of the cone, and when the center of mass is at this point, then omega 2 is in this direction. When center of mass is at this point, then omega 2 is in this direction. So omega 2 is not changing its magnitude, in fact it is changing in direction only. And we know that if this is a vector A which has changed its direction by a angle theta, small angle theta, and this is the new vector A, so the magnitude still remains same, and the change in this vector dA, let us denote it by the small change dA, and this is small angle d theta, then we can say that this dA is equal to a d theta, and dA by dt, which is the rate of change of this vector, is a into d theta by dt, because a is constant in magnitude. Now you can see that the rate at which a rotates is d theta by dt, and I can say that it is a omega. Okay, now in this case also, the a vector which is rotating is omega 2, and it is constant in magnitude, but it is changing its direction. And the rate at which this vector is rotating is d theta by dt, and d theta by dt is obviously omega 1, which is coming out of this plane. Omega 1 is pointing towards u, which is coming out from this plane. So we can say by this analogy that the rate of change of omega 2 will be equal to omega 2 multiplied by the omega 1, which is the rate of change of direction of omega 2. So this is the angular acceleration. Okay, so this result is the result of angular acceleration. And in the other case, let us also discuss this case, second case, first this one. So in this case, we'll discuss angular momentum in later part. So in this case, let us again discuss the angular velocities. So you can say that the cone is now leaning down on the ground like that, with one of its slant height along the ground. And this is the IER, because if the cone is rotating like that, then you could imagine that all these points would be at rest. So this is the IER, and the spin angular velocity of this cone about this axis would be omega 1, and the angular velocity, orbital angular velocity of its VCOM about this axis is omega 2. Now, as we have already discussed in parallel axis theorem, that when an object is not rotating about its COM axis, in fact it is rotating about some other axis which is parallel to the COM axis, then actually that object is under the state of two motions, which is the combination of translational as well as rotational motion. That rotational motion of that object is along an axis which is passing through its COM, and the translational motion of that object is the motion of its COM about the other axis, which is parallel to the COM axis. So what I am trying to say, that I have made these two views of the cone. This is the initial view, and finally after half term it would be like that. So you can see that this line, this diameter line is like that, and after a half turn it would be like that. So you can imagine that the cone, the base of the cone is a ring, and this ring is rotating about this axis like that. And the rotation velocity of this ring would be the same as orbital angular velocity, which is omega 2, because as this center of mass would cover the half circle, then it would also turn by 180 degree. So their half time period is same, and therefore their angular velocities are same. So there are three types of motion which this cone is performing in this case. The first motion is the spin motion along this axis. The second motion is the angular motion, the rotational motion about the COM axis, which is passing through the COM like that. And the third motion is the orbital motion of the COM about this axis. Okay, but we would not add up these omega 2, and we would not say that these are 2 omega 2. Okay, because we are saying that omega is same of both the motions. So the net angular velocity about any of this axis is same, omega 2. Okay, now you can see that as we already have discussed that the resultant angular velocity should be along IAR. So if this should be the IAR, then it means that the component of this omega 1 along this line, which is omega 1 sine theta, is cancelling out this omega 2. So we can say that omega 1 sine theta is equal to omega 2. And the omega resultant is only omega 1 cos theta. Okay, so these are very important two results which are obtained in this case. And you can see that again we are attempting to find out the VCOM by all three methods. So let us suppose that its center is moving with the velocity of VCOM. So VCOM can be written by this axis, this one. So you can see that this distance is h cos theta. So we can write that VCOM is h cos theta into omega, this omega 2. Okay, and this is omega 2. And omega 2 is also equal to omega 1 sine theta. So VCOM can be written as h omega 1 cos theta into sine theta. In fact, omega 2 is substituted by omega 1 sine theta. So I am substituting it omega 1 sine theta. So this would be h omega 1 cos theta sine theta. Yes. Okay, so this is the VCOM in terms of omega 1. Now if we write down this VCOM through IAR, so again you can see that this distance would be r cos theta, this one. This would be r cos theta because this small angle is theta. So we can write down VCOM as r cos theta into omega resultant. And omega resultant is omega 1 cos theta. So VCOM is equal to r cos theta multiplied by omega 1 cos theta. So VCOM is equal to r omega 1 cos square theta. Now you can see that tan theta is equal to r by h, and you can replace r by this. So VCOM is equal to h tan theta into omega 1 into cos square theta. So this would be VCOM would be equal to h omega 1 sine theta cos theta, which is the same result as this one. So this again proves that there is an existence of IAR, which is this axis. Okay, so now let us discuss the angular momentums of these cases. Now you can see that in the previous case, in this case, we have already discussed that there are three kinds of motion which this cone is performing. The first motion is the spin angular motion about this axis. The second motion is the spin motion or rotational motion about this axis, center of mass axis. And the third motion is the orbital motion about this axis. Okay, so you can see that the angular momentum would be due to this spin angular momentum, and this is LCOM and this is L orbital. So let us write down the values of all of them differently. So we can see that the LCOM is the angular momentum due to the spin of this disk about this axis. So LCOM is equal to, let us also, you can also write down these in vector forms. If this is j cap y-axis, then you can use j cap notation. So LCOM will be equal to ICOM. This is the moment of inertia of this cone about this axis. ICOM about this axis. Okay, so ICOM into this angular velocity is omega 1. So this is omega 1. And L orbital, LO is the L orbital. It is MVR, MVCOM into R. Now R in this case is H. So this is H. And the third one, the spin angular momentum, is LS, and it is equal to ICOM 2. Let us write down the moment of inertia about this axis of this cone is ICOM 2. Okay, which is 3 by 10 mr square. You must have studied this formula somewhere. So ICM 2 into this angular velocity, spin angular velocity, is omega 2. So the total angular momentum, L total, is the vector sum of all these. So this is LCOM plus L orbital, which are in same direction, plus this L spin. So the total angular momentum would be the sum of all these three angular momentums. Now in this case, you can see that when this cone is leaning on the floor like that, then this is the orbital axis, this is the COM axis, and this is the another COM axis, which along which this cone is spinning. So we have already assumed that this velocity is omega 1, I guess, in the last case, omega 2. So this is omega 2. So this would be also omega 2, and this is omega 1. So L orbital will be equal to, LO will be equal to MVCOM into H cos theta, which is MVR. Okay, now LCOM will be equal to ICOM about this axis into omega 2, and L spin will be equal to ICOM 2 about this axis into omega 1. And the total angular momentum would again be the sum of these two angular momentums, vector sum. Now there is a very interesting thing which I would like to point out, that you could not find out the angular momentum, the total angular momentum of this body about this IAR. Because obviously you can see that this is a asymmetrical body. This is not the case which we have studied in the angular momentum topic, that for asymmetrical bodies, the net angular velocity and angular momentum, it is not necessary that net angular velocity and angular momentum must point in the same direction for asymmetrical bodies. Please refer to the video of the angular momentum in the playlist, and you could see that this is a asymmetrical object because there is no mirror image of this object on the other side of the axis. So we could not say that the net angular momentum must be on the IAR. So you could not find the net angular momentum about IAR, and it would be a different result. So you have to find out these angular momentums individually, and then to find out the total angular momentum, you must add them using vectors notation. Now in the history of JEE Advanced, there is only one time in 2016 that a question has been presented on this concept, and let us now discuss that question. Now this is the question which I was referring in the video, and this question was presented in JEE Advanced 2020-2016. Now you can see that this is an assembly of two discs which is connected with a rod, and this disk has a mass m, radius a, and this has a mass 4m, radius 2a. It is rotating and it is spinning about this axis with a angular velocity of omega, and this is L and this is I. We have to find out we have to choose the correct options. So I have drawn this diagram here. You can see that this is the disk of radius a, this is L, this is radius 2a, and this mass is 4m, this is m. The center of mass of this system would be at this point. This is the center of mass, COM, and this distance would be L by 5, and this would be total 9L by 5. Now you can see that sine theta would be equal to perpendicular upon hypotenuse. So perpendicular is 2a and hypotenuse is this one. So this distance you could easily find out that the relation of L and A is given. So L is equal to root 24a. So this distance hypotenuse could be found out by this thing, 2L square, 2L whole square plus 2A whole square. So sine theta would be 1 by 5 and cos theta would be root 24 by 5. Now this system is spinning about this axis with the angular velocity of omega, and we can say that this would be the IAR, this red axis. This is similar to the leaning cone which we have studied in this video. So let us first of all find out the angular velocity of this system about z-axis, which is one of the question. This is the center of mass of assembly rotates with the angular velocity of omega by 5 about z-axis. So let us verify this result. You could see that the resultant angular velocity would be along this one, and this angle is theta, and this angular velocity is omega. So we can say that the velocity with which this system would be rotating, the center of mass would be rotating about z-axis, is, let's suppose, omega dash, and this is the resultant omega. So I can say that the component of this omega about this line is omega sine theta, and omega sine theta will be the z component of this velocity, and it would be cancelling out this one. So omega dash will also be equal to omega sine theta, and therefore omega dash can be seen as omega by 5 because the value of sine theta is 1 by 5. So this option A is correct one. Now let us discuss the angular momentum. Now to discuss the angular momentum, we could not use the approach of IAR, which we have already discussed in this video. Okay, now you can see, firstly you have to analyze carefully that how many motions are there in this problem. Now you could see that I am erasing this part. We have already seen. Now you could see that there is a motion. You can analyze that about this axis. It is spinning, so there would be a spin angular momentum, LS. It would be I omega, and I would be, this is ma square, this is a disk, so ma square by 2 plus this is 4m 2a whole square by 2 and into omega. So LS would be equal to, you can see that it is ma square by 2 plus this is 8 ma square into omega. So this is 17 by 2 ma square. But and in this problem, the option C is given as the magnitude of angular momentum of the assembly about COM is 17 ma square omega by 2. But this is not the correct answer. J has given the answer as A or C. So they are giving the marks to those students also which have applied this C answer. But C is not the correct, because this complete motion is out of the curriculum of JEE according to them. So you can see that in these case there would be a motion of this system about this axis also, with the angular velocity of this omega dash, which we have already calculated, and this omega dash will be equal to omega by 5. And this complete system is rotating about this axis also. So this is the rotational angular momentum. So let's suppose that this angular momentum is L com dash. So the total L com will be equal to L spin plus L com dash vector sum. So this would be the total angular momentum of the system about com. You could find out this angular momentum by using I omega. You could find out the moment of inertia of this disk about this point, this axis, and then you can apply the parallel axis theorem to come to this axis, and then you can use this omega dash. So this L com dash would be I about this axis into omega dash, which is omega by 5. So so to say that the angular momentum of this system about com is only this would be the wrong choice. So I think, and according to me, this should not be the correct answer, C. But JEE has given the correct full marks to those students also which have marked only A, because according to them C option is also incorrect in a sense. Okay. Now let us find out the angular momentum of the entire center of mass of this assembly about the point O. So to find out this angular momentum, let us see. I am again erasing this one because this figure is on this page also only. So now you can see that this center of mass is moving with some velocity vcom, which we can find out by IAR concept, that vcom is equal to r dash omega about, and r dash is the distance of this center of mass from IAR. This is r dash. So this is the vcom, and omega is the omega resultant about this axis. So this is omega resultant, and omega resultant would be omega cos theta. Omega resultant is equal to omega cos theta. So vcom will be equal to, you can see that this is r dash and this is 9L by 5. So r dash is equal to 9L by 5 sine theta. R dash is equal to 9L by 5 sine theta. So vcom is 9L by 5 into sine theta, and omega resultant is omega cos theta. Okay, now we know that L about O, the angular momentum about O, would be mvr. You could imagine that vcom would be inside this plane and this is the r. So vcom is perpendicular to this distance r, 9L by 5, and hence their angular momentum would be pointing like that. I'll show you that this angular momentum would be pointing like that, LO. Okay, so this is LO, and LO would be m vcom into this distance, which is 9L by 5. Okay, so m is the total mass of the system, which is 5m. So this is 5m into vcom. Vcom is 9L by 5 omega sine theta cos theta, and this is vcom, and this is also 9L by 5. So this is 9L by 5. So you could see that LO is equal to, this is 81 ml square by 25 omega, and this is cos theta is root 24 by 5. So I have used that 5 to write it as 25, and sine theta. Okay, so you can see that L sine theta or you can again write it down. You can see the option that it is 81 ma square omega. Okay, now you can see that this is sine theta, and the value of sine theta, I'll write the value of sine theta also. So value of sine theta is 1 by 5. So here would be 5. So LO will be equal to 81 ml square omega upon 125 into root 24. This is LO. Now we have to represent the answer in terms of L and in terms of A. So you can see that L upon A upon L is tan theta. So tan theta is equal to A upon L. So I could substitute the value of L as A upon tan theta, and the value of this A upon L is given as 1 upon 24. So A upon L is 1 upon root 24. So this would be A upon tan theta, and this is A upon root 1 upon root 24, which is root 24, A root 24. Okay, this is given in the problem. Okay, so it is already given in the problem. We need not to substitute this value, so we can directly substitute the value of L. Now this is LO is 180. LO is 81 by 125 ml square omega. LO is 81 by 125 ml square omega, and into root 24. The value of L square will be A square into 24. So it would be LO would be equal to 81 by 125 ml square ma square into omega into 24 root 24. Okay, so you can see that 24 root 24 is approximately nearer to 125, but it is not exactly 125. So we could not say that LO is 81 ma square into omega. So this option is incorrect. Option B is incorrect. And the magnitude of angular momentum of assembly about center of mass is 17 ma square by 2 is also incorrect with respect to as seen by me. And the magnitude of Z component of this L is 55 ma square by omega. So if you have to find out the Z component of this net angular momentum, then you can see that there would be angular momentum which is spin angular momentum. And if we have to find out the net angular momentum about Z axis, then this angle is theta and this angle is 90 minus theta. So I can say that LZ is equal to LO cos theta. This is LO cos theta minus this would be equal to LS sin theta. This is LS sin theta. And LS we have already calculated that LS is equal to this 17 by 2 ma square. I've written it. So it is 17 by 2 ma square omega. And LO we have calculated this. So if you will substitute these value here, then answer would not be equal to 55 ma square omega. So D is also incorrect. So according to me, option C is not correct conceptually, but JEE has considered option C, and in fact JEE has given the complete marks to those students also which have ticked the option C, because they consider that it is far beyond the scope of JEE Advanced to analyze this COM about this axis. So they have rewarded those students also. But conceptually that is the not correct answer. So this was the complete analysis of the rolling cone motion. And I hope that you are enjoying on our channel Tesla Adventures, and day by day I am always longing to improve my channel, and please support us by subscribing and spreading the awareness to other people also, so that they could also get the complete systematic preparation of JEE Advanced in physics subject. Thank you.